Okay, so I can see who is on next, Catherine or Annie.
I think Annie's first.
Okay, Annie, got a question? She might have stepped out for a second. Then, Catherine, if you had something to ask.
Okay, I have a specific problem. It was one of the, I think it was the last homework you posted.
Okay.
It was it was homework. It's labeled as class 12, but it's due next month.
Okay.
So it's the pinball problem, and I kind of have worked my way through it, but initially I was having trouble with where to start. So if we could go over the pinball problem where there's two pinballs and they uh, collide.
Can you tell me where it is in the? Is it
Yeah,
is it under one of the classes?
yeah. Give me 1 second. I think it's the last homework problem. Online homework from 314.
Nope. Okay.
Oh,
Oh,
sorry. That's a video. My bad. Um, class 12 homework 426.
okay. So this would be back in under class 12.
Class 26, actually.
Oh,
But
okay.
it's
Sorry.
labeled class 12.
I wonder what I did there. Class 26.
I think it was a homework.
Oh, I see. Yeah. Okay, that might have been a leftover thing that. Um, oh, I got you. These were ones. I'm sorry. These were ones I posted because they were just on old things. Try to get you remembering back to all your stuff with. Gotcha. Yeah. Okay. Yep. I see now. Sorry. Yeah. So let me. I'm gonna make a little new sheet here, and then let's just copy this on. Um, Yeah, so this one I put up just so you could get an idea of, some kind of trying to start remembering your things of um, particle things again, because it had been a while since we looked at them. So let's see if this, okay. So, all right, so this one it's starting out and it sends a ball A into action and it hits a second ball B, right? So be it both of these masses weigh or 80 grams, and the coefficient of restitution is 0.8, right? And then so basically what we're saying is we've got this mass of A is also equal to the mass of B, which is 80 grams, right? Did you have a specific question on it, or do you just want to talk about it in general?
I just kind of wanted to get walked through.
Okay, so then what do you think would happen? Well, how would you start this thing off?
So, my first attempt at it, I was looking at work energy,
Mm-hmm.
and because there's 4 or 5 work and potential work energy um, sides of the equation, and I was looking at A with respect to the spring before everything starts,
Mm-hmm.
and I got kind of lost at where, because there's so many variables there.
Yeah.
So I realized later that if you start at when B is horizontal,
Mm-hmm.
it's a little easier, but I went through and I was trying to solve it from point A initial.
Yeah, so I guess I would probably agree with you that it might be a little bit easier to kind of start like here, and maybe we call that position 3 and call this like a position 2. And what you could then start doing is saying, okay, what is my required speed, right? Because it asks you to find what is the first thing it asks you, how far do you have to pull back the spring so that ball B just reaches a horizontal position. Okay, so you can figure out from that exactly how fast B has to be moving to reach point 3, right? Does that
Yeah.
make sense to you?
Uh-huh.
Okay, so then we could do that one with what approach?
Um, we should be able to do work energy
Hmm.
from all of the points, right?
Well, you got to be a little careful, right? Because you can do it from like where B is, but what makes B start to move?
The velocity of the other ball, so an impact momentum.
Yeah, okay. So you got to remember that like you can't just do energy through it because what happens during an impact,
There's a coefficient of restitution, right?
right? And what does that kind of mean physically about
Um,
energy?
it's not a perfect
Hmm.
translation of linear momentum, right? There's
Well, you
B
have
getting some of the energy and A is receiving or keeping the rest of it.
yeah, so but remember in an impact you always lose some energy,
Mm-hmm.
right? So you couldn't say just look at the energy of A and say it's all transferred to B.
Okay.
Okay. So what you just said about going though from sort of this position 2 to position 3 is perfect, right? So you could even, if I set a datum right here, right? So if I set my datum there, then I can go through and say, well, position 2, right? And the only things I have are T2, right? Because I don't have the spring in this. So now I'm just really looking at ball B. So T2 plus VG2, and there's no spring and there's no extra work. So I'm going to take a shortcut here, right? Does that make sense that everything else is kind of going to 0 for sure?
Yeah.
Okay. And then anything up there that I just drew, do any of those terms go to 0?
Well, since it's at horizontal, isn't that like a turning point? So T3 is 0.
It is because it's saying it just barely reaches a horizontal and that's going to go back down. Yep. So that's going to go to 0 because it's just reaching the horizontal. Okay.
And
Anything
then if
else?
our datum is at the floor, then VG is 0.
Great.
So,
Okay.
yeah.
So this ended up being kind of straightforward, hopefully, that this one would be okay. And I'm just going to do, since the M's are all the same, I'm just going to say M equals MA equals MB.
Okay.
Okay. So now we have this one where I'm going to call this VB2. And what that VB2 is going to be, that means immediately after the impact.
Okay.
Okay, so then I have 1/2 mVB2 squared is going to equal just the m times the g times h. And then in the problem, I also gave you, I think that the L was that 1? 20 centimeters, sorry, right?
Mm-hmm.
So this L is going to be, right, that L equals 20 centimeters.
Would you recommend like converting all of these to meters and for the K Newton meters instead of millimeters?
Yeah,
Okay.
yep, I would. Okay, so then basically you can cross that out, you can cross that out, and it makes sense now. You can just get, in the end, you can get a VB2 is going to equal square root of 2 times G times that L, which we had from right here.
Okay.
Okay, so this is immediately after the impact. Is that good?
Yeah.
Okay, so now what am I going to do with that?
Shouldn't is that the velocity? Sorry, the impulse momentum equation. So, VB one or VB A plus VB or sorry.
Yep, you're on the right track.
So the mass of the velocity of A plus the mass of the velocity of B initial equals the mass after the impact of, or the, sorry, mass times the velocity after the impact of B
Yes.
and the mass times velocity of after impact of A.
Yeah, and what you really are going to need to do to start that out is to do out your do an impulse momentum diagram.
Okay.
Okay, so um, you'd have this, and what's VB1? This would be right before the impact when I said VB1. So what is it right before the impact?
0.
Yeah, good. And then we have, for my impulses, what would I put there?
It would be equal and opposite, right?
Yeah, perfect. Okay, so we have this. Now the other thing that gets a little tricky is I also have some sort of T delta T that I would draw in, because I could end up having some sort of tension impulse in the rope.
Okay.
Okay, in this case I won't, but if the ball was like going downward at an angle or something, then you could think about how that might jerk the rope a little bit.
Okay.
And then right after that impact, now I have, right, these things where I've got MVB2, right, and I've got MVA2. Is that okay? So that's right after the impact is this 2-part. Is that good?
Yeah.
And I'm going to define this as my positive direction. So you still have to define a positive direction. Okay? So then, now that I've drawn this out, now I can do that step where you were saying, but you need to make sure you draw those diagrams. Okay? So we've got it now. We can say, all right, well, MVA1, and then you told me, right, that this was 0 because it was sitting still, is equal to M times VA2 plus M times VA3. Is that okay?
Yeah.
No, it's not. I screwed up. What did I do wrong?
Shouldn't it be the B after impact and
Yeah.
instead of
Thank you. There we go. Now is that okay?
Yeah.
Okay. So now that I look at this one, right, so I just did that in the X direction essentially, right? I didn't really have the momenta in the Y direction. So I'm just looking at this in that X direction. Okay, and I know what this VB2 is, right?
Yeah.
Because I found it right over here. All right, but I don't know what, I found that right over here, but I don't know what VB, what this other one is here. This, I don't know VA1 or VA2. All right, so what's another relationship I might be able to use to find that?
The coefficient of restitution.
Yeah, perfect, right? So I've got this E is going to equal, and now I can do like VA2 minus VB2 all over VB1 minus VA1. Okay, and then basically I knew what VB2 is, right? Because we were given this. Do I know what VB1 is?
It's 0.
Yep, that one's 0. Okay, and then I know what E is. So basically between this one and this one, I have 2 equations and 2 unknowns. Right, I have VA1 and VA2.
Mm-hmm.
Does that make sense to you?
Yeah.
So now I can solve that. Right, I can solve now for VA1 and VA2.
Okay.
Okay.
And then once you get VA1, you should be able to plug that in to work energy equations to find the distance the spring is compressed.
Correct.
Okay.
Okay, so tell me how you started thinking about it, Catherine. Tell me again what you had done?
So the first try, I was looking at A and how it had potential energy and then transferred into kinetic energy with a work energy lens. So it would just be the step that we would now do instead of, I was starting with that. And it was a lot of extra variables and difficult to
Yeah, I mean, but it's still kind of similar type of stuff, right? I mean, it just might not go quite as easy as you're looking, right? As what we just did, but you would still have 1/2, kind of a kx squared that you would do, and really all of that's going to go into the 1/2 m times VA1,
Okay.
right? So now you would be able to solve that for the VA1 squared,
Hmm.
right? So you now have like a VA would end up equaling square root of what, kx squared, right? That's all it would be, isn't it?
Yeah.
Okay, so then that you would kind of plug into here, and then you'd also have it because this is VA1 like we talked about. It could also go into there, so it does get messier, like what you
Hmm.
were saying, right? Because
Oh,
you'd want to eventually solve it for the x.
we are missing a mass underneath kx.
Oh yeah, thank you. Yep. Okay. So yeah, it can really help out a lot more, like what you were saying. I think if you can figure out, which one to kind of work backwards. And remember we did sort of work backwards when we did the whole car crash stuff too, right?
Hmm.
Okay.
Okay. Thank you.
And did the second part make all right sense too? Did we have one more? How you could figure out the force in the string?
You should be able to plug in. Oh, the force in the string. Actually, I didn't start that one.
Okay. Why don't you want to look at it?
Yeah,
And see
I'd love to.
okay. Now I was saying, do you want to look at that on your own, or do you want to talk about it real right
Um, could you tell me how to? What? Actually, I think I know how to do that one. Yeah.
Okay. Why don't you think about it, and then if we want
Come
to,
back.
if you want a question, yeah, I'll let somebody else ask a question.
Okay. Thank you.
Sure. Um, Jackson, looks like you were on too. Do you have a question?
No, nothing yet.
Okay. Abdullah, you said you had a second one, right?
Yeah. So for the, I think it's like let me see what it's called exactly. It's called the more review for final with solutions.
Yeah. Give me a second.
Um,
I think I've got that.
it's not. I mean, I guess it's just like a conceptual question about something. But yeah.
Let's see if I can get a new share up here. Okay. So can you see that now?
Yeah.
Okay. So what was your question?
So for the hemisphere one, we can't just use parallel axis, or can we? I guess use parallel axis theorem to find the moment at A, or to find the moment of inertia at point A, and then just use that as opposed to using the moment at the center of gravity, or like the moment of inertia in the center of gravity.
Well, the problem here is the only way that you can, the only time, and I think actually Jackson, you might even had this question at one point about using that bottom point, or somebody back in your corner there on your team, where the problem is that's only true at point A if there's no slip. So if point A is slipping, then you can't do that. Some moments about A equals IA alpha. And that's why I don't really usually teach that for something that's rolling. If it's rolling, we pretty much always did some moments about G.
Okay. So when it says though, it starts to roll without sliding, does that mean that we can use it in this instance?
Yes. Well, the minimum value for which, yeah. So Abdullah, I don't like to tell you to do that because I think it can just get you into trouble. I would just say don't.
Okay.
Yeah, I mean, I don't want to say that you can't, but I also don't want to guide you so that you do that on a test and you get, only half credit. So if you're doing a rolling type of problem, I pretty much always go to the G, right? And the only thing it's going to mean, so I would much rather you do G and maybe mess up some algebra than to totally get it wrong. You know what I mean?
Yeah, for sure.
So you can work through it both ways, and if you feel comfortable and are really feel strongly that you can do it both ways, that's I'm gonna leave that up to you. But I would be really, really careful.
For sure. Yeah. I mean, I guess my question was, can you? Because I remember there's can you consider as a fixed axis for that certain point in time?
Yeah.
But yeah, I mean, for sure, I'll take your advice on this.
Okay. And then what is your Annie's asking, what's your kinematic constraint here, do you think?
Only in the x direction.
What is?
Or well, point A would only actually. I'm not sure. Oh, isn't it oh yeah. That's actually my second. Well, yeah, that's actually kind of the same question I have. Whether the negative r alpha is from point O or from the center of gravity.
Yeah. So do you remember how we we almost did a derivation for that? Do you remember how we ended up saying for the how we got to that? We started out and we said, okay, well, how far does that thing go? Well, it's like an S equals R theta, right? And then we said, well, the V is equal to R theta dot, right? Which is equal to R omega. Okay, but that was when we had kind of this full circle, right? And for almost all of our problems we've done, O and G have been the same. But I did sort of put you to one problem in the book where I think it had I don't know, some sort of hole thing kind of cut out like this, I think. And then there was also one example problem I gave you where I think it had a bar welded onto it like here. So anyways, so what do you guys think? Is it going to be, what is that, the velocity of? Is that going to be the center of mass or the geometric center of the wheel?
The center of mass.
And I think it's going to be the center of rotation.
Okay. And what do you think? Center of rotation. So what was that? Is that point A, point O, or point G, Jackson?
Point O. Yeah.
So the center of the kind of the geometric.
Yeah, I guess. Yeah.
Okay. So this one's going to be then A of O is going to equal minus R alpha. Okay.
Oh, wait, so it is the geometric center?
Yeah, got to be the geometric center for that wheel. So it doesn't matter if there's a bar there or if there's a hole there or whatever. It's always going to be, your geometric constraint is going to be this guy here. And that's of the center.
Geometric center.
Yeah. Okay, because I think how we did it when we first kind of did the kind of looked at that whole derivation, right? I kind of asked, well, how far would this whole thing move, right? If it goes around, some angle theta, and so it doesn't matter if there's a bar welded to it or anything. That part doesn't matter, Annie. It's still going to be the same kinematic deal right here, because it's all about how the wheel moves, right? So the wheel doesn't care if there's spokes on it. The wheel doesn't care if it's a bicycle wheel or a car wheel or whatever, right? It's still going to go around one whole revolution, right? It's going to go around the circumference, right? And if it just goes around, this far, it's still only going to go around S equals R theta, right? So it's only going to roll that much, and that's as far as the center of the wheel is going to go.
Yeah, the whole circle really ties in. I like drawing out that circle. Yeah, that totally makes sense.
Yep. And then if you have a hole or a bar or whatever, then it's going to affect kind of two things. One is where your overall CG is located, right? So when you do sum of forces in X, you've got to do that for that particular point, right? So it's going to change your I, just like your I changed here because it wasn't a disk. And then it's also, you're going to end up having to do like A of G is equal to, and now what you know is A of O, right? Because these two are going to match up.
Okay, yeah.
Okay, and I think that's, trying to remember where's that one? Okay, yeah, and so this is essentially what we did here, right? So these are that whole solution that I posted is based on just what I had written up, where I said, hey, this is A of G, right, equals A of O minus the omega squared RGO, or what we've usually done is omega cross R.
Yeah. Yeah, I mean, I was a little confused for the answers, but I mean, I think this clears things up.
Okay, good.
Okay, well, just as a general question, are the questions that you give us like harder than what we should expect on the final?
Well, I mean, generally what we do is sort of a little range where, we might have, say, we've talked about kind of four basic things, right? We've talked about kinematics, we've talked about impulse momentum, we talked about kind of F equals ma, and we've talked about work energy. So usually on these we say, okay, well, let's do, an easy work energy-ish one, and then let's do a medium level, kinematics, and then let's do a hard work energy and, combined work energy kinetics type of thing. So I can't quite answer that, you know what I mean? Because some of them will be about the same and then others will be harder, but it just depends on which kind of type of problem we're looking at that particular year.
Okay, for sure. Okay.
Annie, you're asking about the minus, and that's because of where the IO that they had kind of original because your IG, in this case, this was kind of your IO, and then you're moving the G is over there. So the IO is actually the one about the very center of it. So you don't really have to worry about it. That's why what we gave you the ones here. So IO is what's really equal to a 2/5 mr squared if you did out the full, derivative, if you were going to do a integral to get that whole thing. So then if you were doing the parallel axis theorem, it's IO equals IG, right, plus MD squared. But what we really want in the end is IG, because that's what's in our, right, that's what's in our equations of motion. So basically you get in this case that IG is equal to IO minus MD squared. Do you see how the algebra works out there, Annie? That's correct, but that's about its center, right? So the I for a sphere is 2/5 mr squared, but it's about its center. So that's why I said IO is 2/5 mr squared. Right? About its center, but we need it at G. Yeah. Okay, more questions.
My roommate's left, so it's a little bit quieter now. I can talk.
Okay, good.
Could we ask you questions about the concept warehouse stuff?
Yeah.
Okay, let me pull that up myself. Um, so I was looking, let me log back in. I mean, I guess number 19, and I'm pull that up right now, but I just write that down.
Were you still getting ready to ask something?
Yeah,
Okay,
I'm
you
just
just-
pulling it up right now. Okay, yeah. So, I mean, I think this is actually a quiz question that you asked us like earlier, or the second or first or third quiz or something like that. But it's, so I don't know if you have it pulled up or if I should.
Well, for these, what I do, Abdul, is it's more like I talk about the general concepts because I use this thing quite a bit for, that I don't like to post exact solutions for these because then when stuff gets out, I can't really use it as a decent metric anymore.
Okay, yeah, for sure. I mean, I was just trying to figure out the like conceptual portion of this, anyways.
Yeah. So why don't you tell me what the problem's like, and then I'll give you something similar, probably.
Okay, so it's saying, referring to the figure below, if you are walking radially inward at a constant speed relative to a platform spinning counterclockwise
Sure.
at a constant speed
Yeah.
relative to the ground, what is the direction you will experience?
Yeah, so we worked a bunch of these, right? So you've got, it was actually I think it was even on the midterm, right? So, and in class, we worked it kind of 3 different ways, right? So what type of problem do you think it is to start out with?
Well, I mean, it's a kinematics type of problem.
Right, and then what type of coordinate system would you use?
The polar.
Okay, and so let's just do sort of one kind of in general here, right? So if we have something like this where you're walking out and then you have a, some sort of a, I don't know, maybe your omega's going like this.
Yeah.
Okay, so basically here's your center, you're walking out. Then the couple different ways you can do, right? So first of all, if you're out here, right, then what type of acceleration do I always have?
Inward.
Yeah, so I'm always going to have some sort of centripetal acceleration that's going to go inward, right? And then the second part is you're going to have a Coriolis type, right? So you can look at it in a couple ways. One is I'm going this way, and then just a second later, I'm going this way, right? Because I'm turning around. Does that make sense? Because I'm walking kind of on a line, basically.
Yeah.
Okay.
Well,
so
if you don't mind,
the difference is that way.
Well, if you don't mind, could you do it going counterclockwise? Because that's how the problem is set up.
Right. That's what I was saying before. So I do mind because I want you to just figure it out in general, right? I don't want to have because I'm posting this video, so I kind of don't want the exact answer out. So
okay.
Right. So you should now be able to do it anyway after this explanation.
Okay.
So then, right. So that's one way to do it. You got that?
Yeah.
Okay. So then, right, then what you can look at it is there's a second way, right? So we could also if we go right to the equations, right, then we have like an r double dot minus r theta dot squared. That's E sub r. Right, then we have a r theta double dot plus 2 r dot theta dot E sub theta. Okay, so my R, right, I was walking out with some sort of R dot, right? So the R double dot was 0. Is that okay?
Yeah.
Okay, then this guy is what we got for our centripetal right there. Right, and that's what you already told me. Hey, that's going back into the center, right? I've got one definitely that's going this way.
Yeah.
Okay, then what you can do is let's look here. Well, that's 0 because I'm going around at a constant angular velocity. Is that good?
Yeah.
Okay, and then if you remember from how we do our angles, right? This is theta, and this would be like an E sub r, and this would be like E sub theta if I was setting up my coordinate system.
Yeah.
Okay, let me make that in blue so it's a little bit different there.
Doesn't E sub theta go in the direction of like how your angular velocity is going?
You can do it in a couple of ways. So for this one, right, so one of the conventions is actually what I've just drawn here. So I'll show you what you could do with yours in just a second.
Okay.
Okay. So in the one that we've just drawn up, I don't know why the red popped up. The one that I drew up right there, right, then the R dot, is that R dot plus or minus?
Be positive.
Abdullah, do you see that? Because the R is getting bigger.
Yeah.
Okay, so that would be plus, and going here, and then is the theta getting bigger or smaller?
Well, because we're going clockwise, it's getting smaller.
Yeah, so then this is going to be a minus. Okay, so positive times a negative is a minus, so that points in this direction, which is the exact same thing as that I just told you before, right?
Yeah.
Okay, so then, Andy, to your question, even if I decided that E sub theta was going to go this way, right, then this omega would be going the same in that direction. So then this would be a positive here, right? The theta dot would be a positive because that's the direction that this is going in. So I still get it pointing in this direction.
Okay, that makes sense.
Okay. Then the final way you can look at it, right, is, so I can get rid of these guys. So I think that'll hold. Let me get rid of that too. Okay, so now what we could also do is, so let's say I'm right at this point, and then which way is my tangential velocity right there because of the omega?
Perpendicular to that point.
Yeah, so it's going to be something like that, right? So that would be like my little kind of V tangential. Okay, and then what happens though, because just a second later, my R is bigger, right? If I've walked like a little bit, right?
Yeah.
So then if my R is bigger, what's true about my tangential velocity?
It's also bigger.
It's also a little bigger, right? So that change in magnitude is this difference right here, right? And it's also going that way, right? Because we shrink all this stuff down into, infinitesimal steps type of thing.
Yeah. Okay, so in this case, so you'd be experiencing a positive acceleration in the ER direction.
Negative. You told me before, right? It's pointing.
Yeah, I mean, wait. So if you were walking outwards, though, wouldn't that kind of just like cancel out?
No, because I'm walking at a constant velocity, right? So if you remember the walking that way, right? Centripetal acceleration is all about the change. So if I'm right here, right? What happens? Why I have centripetal is because at first my tangential velocity was pointing that way. Then just a second later, I drew it the wrong way. Hold on. If I'm walking, then at first my tangential acceleration. Let me start one more time. Hold on. I'm going to just rewind. All right. So if I'm going here, then my tangential velocity is that way, right? And then just a second later, because I rotated around a little bit, my tangential velocity is that way, right? So the difference between those two always points back towards the center. So that's centripetal acceleration, which is essentially this term right there. And it doesn't matter how fast I'm walking out. I'm always going to have that term pointing back towards the center. Now, if I'm running and accelerating out towards the end with an R, some sort of R dot dot, then it could be that R dot dot is bigger than the R theta dot squared.
How would we know which one outweighs the other? Would that have to be specified?
Yeah, you have to calculate that.
Okay.
Wait, so if he's walking outwards with a constant speed, but then he's experiencing this acceleration, doesn't that mean that he should start like slowing down and start falling back in towards the center?
No, because that's all about, remember, there's two parts of acceleration. There's a magnitude and a direction. So this centripetal part right here is really all about your change in your direction, like what I just showed right here.
That's right, yeah. Okay, and so you'd have a negative acceleration in the E hat, like E sub R hat direction. And because of our coordinate system, we'd also have a negative E acceleration in the E sub theta hat direction.
That's correct.
Okay.
So I have a question that's a bit related. It was a question on the exam, and it was, if I can remember correctly, it was the one with the robot arm whose theta was decreasing and whose R was decreasing.
Okay.
And the question asked about the directions of the forces. And so I did like an FBD and a KD, but that ended up getting me the wrong answer because I don't know. So I talked to someone who'd gotten it right, and they said they just used the acceleration equation to tell like negative R theta dot squared and 2 R dot theta dot.
Sure. What causes accelerations?
Forces.
Right. So if sum of forces in AR, right? So I mean, basically, I just use Newton's second law, right? And I can put the vector over there, right? So wherever, if my net acceleration's going this way, then my net force has to go that way as well, right? If my net acceleration is going this way, then my net force has to act that way as well. So it's just same directions.
Okay.
Okay, did Catherine or Jackson have anything too?
I'm just absorbing everything.
Okay. Jackson, you got anything?
No, kind of just following along. I'm going through all my old quizzes, but nothing really stands out yet.
I was wondering, is there a way to get a hold of the dynamics concept inventory questions, like to go over them again, or no? Because I was going through them, or I tried to look at it, and it says there's no current questions.
Right. Did you already take it the second time?
Yeah.
Yeah. So on those, what I want for those, Andy, so there's a couple of things. So I actually look at those and sort of compare to see, because I change things up. I mean, I've taught this a lot, so I like to do, try out different things. So then I use this DCI to kind of help see, if things have worked. And I actually present this type of thing at conferences because other people are interested in how students learn dynamics, and we want you guys to learn it as well as you can. So so basically I don't give printouts and really go over them. I'm always super willing to do like what we just did with Abdullah, but I don't have them kind of available because once they get out I can't use it as a tool anymore.
Right. No, that's totally okay. But is there no way to go back in and look at the questions to study?
Right. I mean, basically what I'm hoping you guys will do is just kind of write down little parts of what you might be confused about, like what Abdullah was asking there.
Okay.
Okay. Any more questions?
Yeah, if nobody has any, can I ask another?
Sure.
So this is also from the concept warehouse one, and it's about like a crate moving to the left. And there's like a bunch of points, like point A, which is at the top of the crate, point C, which is like a third of the way of the crate, point D, which is like all the way in the bottom, like below the crate and the wheels, and then like point B, which is just like far away, but in between point A and C, if that makes any sense or visual sense.
Okay. So is this thing moving to, does it have a velocity to the left?
Yeah. So point A would be at like the top left corner.
Okay.
And then point C would be at like a third of the way from the top, from the bottom of the crate.
Okay. So go ahead. What's the,
So I mean, it's just saying like, it's just asking at what point, so like, yeah, what's the largest magnitude of angular momentum?
yeah. So we did something basically exactly like this in class, right?
Yeah.
Except then it was a sphere.
Yeah.
Or
Well, so it's, I mean, I guess my question is specifically like the main, the R or the MV cross R is always going to give us that MV D perpendicular, that distance perpendicular.
as long as you're doing, yeah, as long as you have a right-handed coordinate system.
Okay. So in this case, then, it doesn't matter how far the point is from like that center of gravity. It matters, or like not far, okay, like, so the point all the way on the ground would create the biggest moment, right? Because it has the biggest perpendicular distance.
Yeah, let me, I mean, so basically depending on how you've defined, like if this is your plus direction, right, then, you know, you can put these points about anywhere you want, right? We did this in class too, right? Like this is the same perpendicular distance as this.
Yeah.
Right. So it doesn't matter really where along this big old line you put your point. Right. And then this is going to be smaller because that perpendicular distance is less. And then if I define this as positive, then, right, because these are all going to have a positive one about this point, positive around that point, positive around that point, positive around that point, whereas it's going to be negative about that point.
Yeah. Because you'd point, you'd go from the center to that point, and then
well, from the point to the MV. Whoops, sorry. Right, so it's from this point to here. So it would be like, if it was that one, it'd be like R cross MV, right? And my R is just like, I don't know, H, that would be in the J hat, cross into M times V would be in the minus V I hat now. And that's going to give me plus H, M, V in the plus K hat direction.
So you have your finger, you have your your pinky side of your hand going from the point to the velocity vector, and then, or the momentum vector, and then you curl your fingers in the direction of which the momentum vector is going in.
Yeah, I mean, it's, so if this is your point, your axis right here, right, then this is on top of it, so it would go that way.
Okay.
Yeah. Just like if it was a force.
Yeah.
Okay. Or you can put your, you know, I think I did this in class maybe where I put my pencil down on here and then I pushed that way, and then you can see which way the page rotates.
Yeah. Okay. Cool.
Okay. All right. Well, I will make a recording of this and place it up. Any last minute questions?
I have a question, but it might not be quick enough, so it's totally okay if it doesn't get answered. But in the concept inventory questions thing, there was a question about like the friction force of a car. There were two separate questions. One had to do with the front wheel and one had to do with the back wheel.
Mhm.
It was rear wheel drive. So I was wondering if there's a difference there between the two wheels.
Yeah, there is. And do you remember when we talked about it by any chance?
I remember it a little bit. I know that we talked about it, but it was a while ago. So
Yeah, so it was basically during that stuff we talked about when we did the spools. Okay, so what has to cause an alpha?
a force or
Mm,
an alpha causes an alpha.
what causes a linear acceleration? We just talked about it with the robot arm, right? What causes accelerations, linear accelerations?
I like what I don't know what you're looking for, like thrust or like
Sure. And a
torque
thrust is what?
or
Thrust is what's Newton's second law,
F equals ma.
right? So what causes EA?
Force.
Forces, yeah. So forces cause linear accelerations. What causes angular accelerations?
Moments.
Moments. Okay, so on the rear wheel drive, what causes a moment on the rear wheel?
The torque.
Yeah, so the motor, right? So let's say this is my rear wheel and I'm going this way.
Okay.
Okay, so there's a torque, right? So that can cause an alpha. Which way would that cause an alpha in?
Counterclockwise.
Okay, so I'm going to have now, if I want to have my, let's say I even did my kinetic diagram here, so I would have an alpha caused by that torque going that way.
Okay.
So if alpha is going that way, which way does my linear acceleration going to go if I'm rolling without slip?
To the left.
Okay, so now I have this acceleration going to the left. Okay, and I can put in my I alpha, right? So what force would cause that to happen?
The friction.
Yeah, so this is what we call traction a lot of times. So I better write that as torque just so it doesn't get confused. So that's the friction, and you can even sort of feel that, right? Like if you're driving in the snow or on the ice or something, you don't get going until sort of the tire grips the road and that force drives you forward.
Yeah.
Okay.
Wouldn't that create a moment to the clockwise though?
Mhm. Right, but what can be true?
That the torque is greater than the friction force.
Yeah, so that, and we found that out even with the other stuff with the spool, right?
Okay.
So then let's look at the front wheel drive, right? And the other thing you can think about is we have a hub here. Well, at the hub, right, with that wheels, then you actually have kind of the rest of the car acting. And we had a go-kart example problem that we talked about briefly in class, and then I posted the solution there that kind of talked about some of these as well. So if we look at that one, right, where now I'm saying, let's look at the front wheel, right? So if I look at the front wheel, which way is it linearly accelerating?
Also to the left.
And which way is it angularly accelerating?
Counterclockwise.
Yeah, so what can cause that moment?
The friction force.
Yeah, so there's actually ends up here, there's a friction force that goes this way now.
Okay.
Okay, but what causes, right? What else do I need though to make this whole system work?
Like on your FBD.
Yeah.
Well, you're missing a normal force and an mg.
All right. But what's going to cause this? What causes that mass times acceleration?
A moment.
What makes the front wheel linearly? There's got to be a force to to push that front wheel forward, right? To make it accelerate forward. So what is that force from?
I'm trying to think. Would there also be torque on this wheel or no?
No, because it's like the front wheel on your bike. What moves the front wheel on your bike forward?
The fact that it's connected
Yep,
to the
to the frame, right?
yeah.
Yeah, so you actually have, in this case, you have like an AX, right? There's basically a pin and a hub there. So this would be going up, and then actually the rest of the bike does this AY. And you actually had that on the rear wheel as well. Okay, but there they acted, goes down, it goes actually to the right.
Okay.
Okay, so that's pretty interesting that the friction acts differently on the drive wheel and the non-drive wheel on the same vehicle.
Yeah. Okay.
Cool.
Yeah.
As long as you're accelerating. If you're not accelerating, then there's no friction.
Right. So the AX and the AY, would they be in different directions on the other wheel?
The AY would still be going to, and we would call that like a BX and a BY. So
Right. Okay.
BX would be going backwards because it's kind of like the rest of on the rear wheel drive, right? The rest of the vehicle is trying to slow you down,
Okay.
but the rest of the vehicle is also pushing down on you.
Okay.
Okay, well, let me, I'm going to head out and I will, it takes, like I think I've told you guys before, a good 30 minutes because it's got to process the whole video thing. So I'll post that as soon as I get it.
Okay. Thank you.
Okay, all right, you're welcome. See you guys tomorrow. Good luck, everybody.
Thank you, Dr. Phil.
Thank you,
You're
Dr.
welcome.
Phil.
Thank you.
You're welcome.